Algebra 1, Chapter 7, Section 5, Exponential Functions. So we've been working a lot with exponents in this chapter, learning all the different rules of how to manipulate them. What we're going to look at now is what happens when the exponent is the independent variable in a function. So they're generally of the form uh, y equals ax or ab to the x. The x is the exponent there. Um, a couple important things. The a value can't be 0 because if it's 0, it's always getting multiplied by the b, which has the exponent attached, and nothing happens. It's boring. Another important thing is b has to be positive, and it very specifically can't be 1. Now let's talk about why each one of these things are true. So if I have y equals 0 times 2 to the x, it does not matter what I plug in for 2 to the x, it's always going to get multiplied by 0, so it just becomes the constant function 0. Boring. Nothing happens. We've already covered that. If, say, y equals 1, and we have b equal to 1 to the x, well, what's x times itself any number of times? It's always 1. So again, it's just going to give me a constant function, which we've already talked about. The idea with the b value being negative is a little bit trickier. We don't like this for a couple reasons, but the main one is if I plug in negative, well, let's get rid of that 2 there. If I plug in a 1, I get negative 3. If I plug in a 2, I get positive 9. If I plug in a 3, I get negative 27. Plug in a 4, I get positive 81. So you can see it's just kind of bounce back and forth between the positives and negatives as it grows. Not very good, particularly because, even myself, I don't really know what happens when I plug in 2.5. It's not even, it's not odd. I don't know if it's supposed to be uh, a negative or a positive. I don't, I honestly don't even know what it's supposed to do there. Probably have to look at that later. So these are all scenarios that we don't like for our exponential functions. It's very common to see things like y equals 2 times x cubed. Maybe you can have y equals just the number itself. And of course, you could have things like something being added inside of the exponent, or after the exponent itself, something could be added in. Probably shouldn't use 51 there. How about 12? So there's all kinds of different things you can do to manipulate a little bit, but the most basic form is just y equals different powers of a number. All right. So let's talk about the graph of y equals 3 to the x. It's always good when you're first starting out to make a table of values for these kinds of things, particularly before you really know anything about what the shapes of these are supposed to look like. Let's go ahead and just play around with it here. Let's plug in some numbers. How about negative 2, negative 1, 0, 1, and 2? Maybe I'll throw 3 in there as well. So 3 to the negative 2 is the same as 1 over 3 squared, which is 1/9. That is a very small number. 3 to the negative 1 is equal to 1 over 3, so 1 over 3. 3 to the 0 is 1, just because everything to the 0 power is 1. 3 to the 1 is 3. 3 squared is 9, and 3 cubed is 27. If I were to put in another one, a 4 there, I would get 81. So you can see, once it starts going into these positives here, 1, 2, 3, 4 as the exponents, it gets really big really fast. Over here, the numbers get as the numbers get more negative in the domain, they get very, very small. Like think about um, negative 10 for my x. 3 to the negative 10. That's the same as 1 over 3 to the 10. I don't even know what 3 to the 10 is. It's gigantic. Where's my calculator? Um, 3 to the 10. I wonder if it even fits on the calculator. It does. So it's 1 over 59,049. That's really, really small, right? I can't even draw for you how small that is. Um, but the basic idea is the more negative your exponent is, when it's just like a nice whole number there, the closer and closer and closer to 0 it gets. It will never actually reach 0 though. There's no exponent of 3 I can give it that would let it equal 0. Because if the exponent represents how many times you're multiplying it by 3, it never actually is getting multiplied by 0. Alright, so we've got some points here. Let's go ahead and make a little sketch of a graph. Now, an interesting thing here is I don't need a lot of negatives because I'm never going to get a negative. If you take a look at all these values here, all the y values are positive. Let's go ahead and plot some points here. At negative 2, it's 1/9, which is very small. At negative 1, it's 1/3, which is pretty small. 0, 1, 1, 3. 2 is all the way up at 9. 5, 6, 7, 8, 9. And just to put the 3 down, it doesn't even fit on my page. This is what the graph looks like. It slowly builds, and then once it crosses that point there, it just shoots up super, super fast. An important thing to note here is this spot along the bottom. I'm doing it in a light green line here. It's almost impossible to see there. X equals 0, we call that an asymptote. It basically is a boundary line. The graph does not cross it. So it starts really, really close to it. You can see it being really close down here on the left-hand side. It's really, really close. It's almost touching it. But it doesn't matter how far negative you go, it's never going to cross that line. It's never even going to touch it. On the right-hand side, it's just going to get up bigger and bigger and bigger up forever. So that's our function. That's our graph right there. A couple little things here. We need to describe the domain. Well, I can plug any exponent in, so the domain is all x in the reals. The one that's tricky is the range. So I'm going to say it's all y such that y is greater than and not equal to 0. Oh, wait a second. I can't believe I did this. I'll write that in black there. That's a horizontal line, so it should be y equals 0. It's always going to be bigger than 0 for this case. So if you've just got a whole number and it's positive there, it's always going to be bigger. Now, this video is getting a little long here, but I do want to kind of show what happens when you have a negative. Like this, the shape is different. If I were to have y equals negative 1 times 3 to the x, it's going to go down forever, and we'd have y is less than 0 in that case. But we'll probably see that in an example coming up.